Hello, this is our Senior Design 2 final video. We are Team 2 with the Unmanned Underwater Vehicle. These are our team members for Team 2. The overall objective and motivation are what drove this project forward. Our objective was to design, build, and test an underwater unmanned vehicle in order to aid in the location and visual inspection of underwater pipes. The motivation behind that was that there are over 730,000 miles of undersea oil pipelines and 550,000 miles of undersea communication cables throughout the world. These cables are broken pretty often, so need to be replaced. But in order to do that, they have to be visually inspected first, and so that's where the idea or motivation behind this project came.
The project implementation is broken up into 3 stages. The first stage is the actual PVC structure. That was done using PVC pipes and cement to have this thing structurally sound. Then a waterproof container was mounted to the box for all of our electronics to keep it out of water and have IP68 standards. That box is also shown in the bottom right picture, and the PVC structure is shown in the top left. The second stage is the mounting of the sensors, camera, and motor. That was done using 3D printed models and zip ties, as well as screws and different types of hardware to mount that to the PVC structure. The third stage is the wiring, and that is shown in the bottom left picture, the middle picture, and the top right picture. And all that was done using terminal blocks and soldering boards to have all the wires ran through waterproof glands on the external structure into the waterproof box for IP68 standards. This video shows the UUV in water. It is being controlled by a user onshore by an Xbox controller. The UUV has 3 motors. It has 2 motors in the back for left and right movement, and it has 1 motor on the top for submerging. As you can see in this video, it is submerged right now and it is moving left and right. The UUV is positively buoyant. Therefore, we do not use the top motor to bring it to the surface. We just use the positive buoyancy to slowly reach the surface.
Currently shown is the wire diagram for the entire system, which consists of 2 main parts, the user station and the UUV. The user station consists of a personal laptop and an Xbox controller, which is connected to the UUV through Ethernet. The UUV itself consists of several ECEs that are controlled by a Raspberry Pi through pulse width modulation to help control the onboard brushless DC motors. Buck converters are also used to provide 5 volts to our sensors and LEDs. Fuse blocks are also used for safety reasons in order to prevent overcurrent from occurring to any of our sensors and sensitive devices. So at initial startup, the UUV is started using a battery remote disconnect, which can be activated just pressing the on button. Okay, so this is the interface for the Xbox controller to the UUV. So for the left joystick, it's going to control the horizontal motors. So pushing up will make the motors go forward. Pressing down will make them go in reverse. So we can also turn it by activating the left or right trigger. Activating the right trigger will stop the right motor and make it go in reverse, depending on how much pressure you apply to the trigger to help it turn right. And the same goes for the left motor, except with the left trigger. The vertical motor is activated using the right joystick. And so pressing up will make the UUV go down. Pressing down will make the UUV go up. You can also lock the vertical motor to keep it at a certain depth using the right bumper. We can also activate the LEDs in the front using the A button, and then deactivate them again by pressing the A button. And then we can also enable the automation using the start button and then deactivate using the start button.
There's software running on both the user station and the UUV. On the user station, we have a main program that receives the video from the UUV and also detects all the pipes. And then we have 3 concurrent programs running in threads. One that updates the I/O with sensor data, one that updates the controller output with the Xbox controller, and also one that sends a global dictionary to and from the Pi back to the user station. On the UUV, there's also software running on a Raspberry Pi. There's another main program that calculates the motor signal that we need to send to the ECE based off the Xbox controller input. And then there are 2 other concurrent programs also running in threads. One that reads all the sensors, the ultrasonic, temp, and pressure sensor, and then one that actually captures the video and then sends that back to the user station over Ethernet.
The user interface provides the user with sensor data as well as video streaming, and during the automation mode, it also provides pipe detection as seen by the red squares on the video stream. Shown is the final design for the user interface, which was updated with light status, horizontal and vertical motor speeds, as well as the automation mode and vertical motor lock status. The previous data that was saved in graphs from the sensors was replaced with just the real-time data being presented from the Raspberry Pi in order to prevent lagging from the video.
So this is a list of our performance analysis. Our claimed deliverables were a refresh rate of 50 milliseconds for the joystick that we were using, a turn radius of 6 inches, forward and backward movement at half a meter per second, detecting a pipe up to half a meter away, and the ascent rate should be around a quarter of a meter every second. The actual deliverable, which we chose to use a different metric just for ease, which was 480 megabits transfer rate or streaming rate. Fortunately, we didn't even have a turn radius since it's able to turn in place. We can just turn one motor going forward and the other one going backward, causing it to just swivel in place. 0.447 meters per second forward and backward movement, which is very close to our claimed half a meter per second. We can detect a pipe up to 1.5 meters away. However, it does range heavily on how clear the water is in the first place. And our ascent rate is 0.12 meters per second, which is when the vertical motor is off, and the positive buoyancy of the device lifts the device to the surface. So here's a list of some of the strengths and weaknesses we had and we came up with as a group. Some of the strengths: aquatic maneuverability. As shown in the performance analysis, we are able to turn with no turn radius. We can maneuver wherever we wanted to from the very beginning, which was very beneficial. Video streaming and real-time data updates. We can actually upload the stream in real time to a laptop or whatever device is handling the UI. Image recognition, which worked in the previous video discussed. Safety, and buoyancy was also a very big strength, as well as safety, since if something goes wrong, we will need this to surface. Some of the weaknesses: waterproofing was quite the issue. We had to patch it up several times. Ultrasonic sensors do not work in the water, or at least the ones we used. There were a few limitations to autonomy, and that was mostly due to just running out of time. Limited control of depth, as the area we were testing only had a depth of 4 to 6 feet. And there were limited capabilities of troubleshooting due to how the size constraints of the box.
There were many challenges and bottlenecks that we ran into throughout this semester's project. For one, the delay of the Ethernet video was an issue in the beginning, where we had about a 1 second lag. Turned out that we needed to compress the file to actually get rid of that lag during the data transfer. We ran into another delay of video again at the end of the semester with our user interface. Whenever we tried to graph the data in real time, the updating of the data constantly caused the video to again lag. We ended up having to remove the graphs because of it. Another issue we had was with wrong motor orientations. For this project, we needed a mixture of clockwise and counterclockwise motors. And although we ordered the correct one several times, the motors that came in all were the same orientation. So it took a long time for us to actually get in the proper motors so we could start testing in the water. Another issue we have is with waterproofing. We thought it would be pretty simple to seal the box and the electronics from water using a proper sealant, but it actually ended up being much more difficult with water still getting inside when we thought we had proper seals. That continued to be an issue throughout the entire project. Some of the future directions and improvements for this project include using stranded wire instead of solid core for ease of wire layout inside the box. We also would use different waterproofing methods to help keep the water outside of the box as well. And then possibly using an external spool to house the Ethernet cable and the recovery rope would probably all be great additions, as well as some other things listed here.
So in conclusion, overall our project expectations were met, but given more time and with the newly gained knowledge from this whole experience, improvements would have been made to the overall design, giving a better sense of waterproofing, motor control, pipe detection, and autonomous following of the pipe. And then here are references. Thank you very much.